Hello everyone, welcome to Codynamics. In this video, we will be seeing how to simulate a rotating fan in a room. So we will be using OpenFOAM for this, and we will be using a method called sliding mesh or cyclic AMI in terms of OpenFOAM. So we will see how to simulate this. We will be using a solver called PimpleFoam, which is basically transient, incompressible, and turbulence based solver. So this is exactly a case which is already available in the tutorials list of ESI OpenFOAM version 2406. I'm not sure whether it is available in previous versions. I'm using version 2406. So it should be available if you are using the same version. Now let's see how we can do this simulation. I will explain it step by step. Now to find the location of the tutorial case, all you have to do is go to the tutorials location of your OpenFOAM, and under that you will be having your incompressible. Under incompressible you will have PimpleFOAM. Under PimpleFOAM you will have RAS, and inside RAS you will be having rotating fan in room. So this is the case that we are going to use. So I'll copy all of these and put it in a new folder. If you are using Linux, you can work through on how to copy and paste it in a new folder. So I am using WSL, and if you are using WSL, you can follow along. If you are using Linux, from this stage, you can follow along. Okay, now I will open my terminal in this location by right click, and I will open WSL here. So this is my way of opening Ubuntu in a certain location. If you are comfortable with any other way, like navigating from the home directory, you can do it. Nothing wrong. So let's start from here. So since this is an existing tutorial case, we will be getting this allrun and allrun.pre files. So let's see what is there in the allrun. If I open allrun, we can see that it is calling allrun.pre. So let's understand what is there in allrun.pre. So here in allrun.pre, we have the usual header files, and we have the copy for rotating fan and room geometry. So this is also from the resources of the tutorials. It will copy from there and put it in the constant try surface folder. Okay, and for meshing we will be doing surface feature extract, block mesh, and SnappyHexMesh. If you have not seen our SnappyHexMesh video already, I will put the link in the description. I highly suggest you to watch it so that you can understand this video better, because I will not be explaining SnappyHexMesh in a very detail. So you can check the SnappyHexMesh basic video, and then you can check here, because in this I will be explaining how to set up SnappyHexMesh for specifically for cyclic AMI and sliding mesh. So just check that video before you continue watching this. If you are already familiar with SnappyHexMesh, you are good to go and can continue with this video. Then we will be force removing all the fields generated by Snappy, which is not needed at all for us. Then we will be running something called the renumber mesh, which will reduce the bandwidth of the matrix, of the mesh matrix. So it might make the computation faster. And then we will do something called create patch. So you will understand what this is. We will be creating two AMI patches to make the sliding mesh possible. So you will understand this when we are doing it. Then it is restoring the zero directory. So basically we have the zero.original, but we want 0. So this command will basically just copy this, paste it here, and rename it to 0. Nothing else. So once allrun.pre is over, it goes back to allrun, and we will be running the case in parallel. So decompose par is run, then the application, which is PimpleFoam, is run in parallel. Then we will be reconstructing it, and then we will see how to do the post processing, like the video which you saw in the beginning. Okay, now let's see what is there in the case as such. So if you open the zero.original, you can find the u, p, which is velocity pressure, and k omega for the turbulence, and nu t for turbulent viscosity. And under constant, we have our dynamic mesh dict, and we have our g, which is gravity. So dynamic mesh dict is where we will be defining the rotation parameters like the RPM and all for the rotation of the fan. Then we have our transport properties. Basically, this is where we will be defining our fluid properties. So we will see here we are defining the kinematic viscosity, which is new, and we have defined it for air, and it's a Newtonian. Okay, good. Then under turbulence properties, we will be defining our turbulence model. In this case, it is k omega SST, and which is like a RANS model. So we are using the RAS keyword here, and we kept the turbulence on and print coefficients on. Okay, that's it for turbulence properties and transport properties. Before we go to dynamic mesh dict, let's check other files. So when you open the system, you will have a file called relative velocity. This is a UDF, so we are not going to look into it in this video. So you just click it and delete it. So right after you delete, you just open the control dict, and you remove the functions, save the file so that it won't cause any issues. Just because we deleted the relative velocity file, we have to remove it from the functions. I'll close this. So now we can start looking at each of the case files. Before doing that, let's import the geometry which was there already. I'll open the allrun.pre and let me copy the first line. I'll go to the terminal, make sure you are in the correct location, right click and enter. So basically that will just create a folder called trisurface, and inside trisurface we'll have all of these geometries which was just given by the copy paste, because it was already there in the tutorials folder and it just retrieved it for us. Okay, now if we want to visualize, actually we can't because it is all zipped file. You can extract, open it in paraview and visualize, but I don't think that is necessary because you already saw what is going to be the output. Okay, now let's see the next file. In this order, it is surface feature extract. So if you see here, we have 6 files. Basically AMI, door, fan, outlet, room and desk. So we can see that from here also. We have AMI, desk, door, fan, outlet and room. Okay, but now we have to extract the features of this to run SnappyHexMesh. So I'll open surface feature extract, and you can see for all of these 6 files, we are extracting the feature with an included angle of around 150. So even the fan is not very complicated geometry. So 150 is fine. Otherwise, the maximum is 180. You can keep up to 180 if your fan is a complicated curve. If it contains very complex geometries, you can do 180. It's okay. But in this case, it's a very simple geometry. So 150 is fine. Now run the command, the surface feature extract, enter, and it will be done. So the next command is also done. Let's go to allrun.pre. The next thing is block mesh. So let me open the blockmesh.dict. I have already made a video on block mesh. This block mesh is fairly simple, so that video can help you. I'll put the link in the description. You can check it out. Okay, so this is fairly straightforward. We are not going to create any patch using block mesh. So this is just like a background mesh for the SnappyHexMesh. So we will be running this block mesh. Once we run the block mesh, the next thing which we have to do is run SnappyHexMesh. But I want to run SnappyHexMesh parallel. So what I'm going to do is I'm going to set up the decompose pardict. We'll open the decompose pardict, and I'm going to change this to Scotch, and I will change this to 8 because I have 8 processors. If you want to understand parallel processing better, I have made a video and you can check it out. I will put the link in the description. So you can see that I have 8 physical cores, so I can use 8, and I personally like to use Scotch, so I remove the hierarchical and I put Scotch here. Okay, I will save this file. If you are an absolute beginner in OpenFOAM and you are looking for a course, you can check out our Udemy course. I will put the link in the description. This will be a great start for you to learn OpenFOAM and advance through it. So to understand what AMI is, I have put the fan and the AMI here. As you can see, The AMI is the cylinder, whatever you can see here. So this is the AMI. This is the AMI. So what this will do is it will enclose the fan, right? It will enclose the fan and it will act as the rotating region. And whatever mesh is there outside the room and everything else, it will be a stationary region. So this AMI, called the arbitrary mesh interface, will act as the interface between the rotating region and the stationary region. So this AMI, the single surface, whatever you are seeing like this, the entire cylinder will be split into two names. It will be exactly the same, will coincide, but it will be named as master and slave, AMI master and AMI slave. What it will do is the master and slave will communicate between each other and it will transfer all the fields like the pressure, velocity, all the information from one cell to another cell within the rotating, sorry, between the rotating and the stationary region. So that is what we are trying to achieve with AMI. So the inside mesh can rotate freely while it can communicate with the stationary domain outside. So it will seem as if only the fan is rotating and not the mesh is rotating. That is what we are trying to achieve here. I hope that is clear. Now we can go to our SnappyHexMesh setup. Okay, now looking at the SnappyHexMesh dict, we can see that the castellated mesh is true, snap is true, but we are not adding any layers. We are just trying to keep things simple. And for geometry, we have input all the 6 geometry just as needed, and it is named appropriately. You can see it is AMI, door, fan, outlet, room, and desk. Everything is tri-surface mesh since we have the STLs. Coming to castellated mesh, we are adding features. So we'll be using the AMI.eMesh, which was generated by the surface feature extract, and we are refining the AMI by 2 and fan by 2 levels. This is like the feature refinement, and we will be refining the surfaces as well. So for fan, we are putting minimum as 2 and maximum as 2. For desk, it is 1 and 1. But for door, outlet, and room, these are just plain surfaces, so we don't need any refinement. But if you look at AMI, this looks slightly different because we are going to assign it as rotating zone. So the level is just like fan, we are putting 2 and 2 for minimum and maximum. You can put more, 3 3 or 3 4 or 4 4 based on your necessity. It's up to you. Now we have to make these things mandatory to make this as a rotating zone. The first thing is face type. This face type is named as boundary so that the solver will understand that this is not actually a wall but it is like an AMI. And the cell zone will be assigned as the rotating zone. This will be the name, and face zone will also be rotating zone. And the cell zone inside will be inside because the region which is going to rotate is inside the AMI. So we have to put this, and that is what we need to set up the AMI as a rotating zone, nothing else. Apart from that, everything is just basic SnappyHex mesh dict. We put the location appropriately to generate the mesh, and allow freestanding zones is false, and no refinement region. Resolve feature angle is also 30 because we don't have a lot of refinements. Like you can see, this is just a hemisphere with a bunch of cuboids, nothing much to refine, and no layers also. So this is pretty straightforward and pretty simple also, and nothing complicated to understand except for this small region. If you understand this, you are good to go. Now we can generate the SnappyX mesh in parallel. So I will go to my terminal and I will run my decompose par. Okay, now I can run the SnappyX mesh. So the command is npi run np8 snappyhex mesh parallel override. So I have 8 cores, so I'm using 8. If you have less or more, you can use it accordingly. So I'll get back to you once the meshing is over. Now the meshing is over. Next thing what we have to do is reconstruct everything inside the constant folder. So it is reconstruct par mesh constant. Okay, it is done. Now we can delete all of these processor folders. It's not needed anymore. Okay, now the next thing which we have to do is, if you check the allrun.pre, we have to do the renumber mesh. So let's do it. Renumber mesh and overwrite. You can see that it will reduce the band of the matrix. It was initially around 109,000, but now it's 2,992. So that is good for the computation. It will be much faster. I'll clear this. Now let's see the mesh. Next thing what we have to do is create paraview file. So I'll do touch space para.foam. It will create me a paraview file. Okay, we got the mesh. I'll hide this. You can see that we have our desk and we have the fan here and we have the AMI. So these are faced with edges. You can see the mesh is okayish. It's coarse, but it's okay. See, this is what I said. We have two surfaces, AMI and AMI slave. Now what we have to do is do create patch overwrite. So let's go to our create patch dict. You see here we have a set of commands. You don't have to worry about this. Go to patches. Now the first thing is name is AMI1. Patch info. Under patch info, the type is cyclic AMI. That is what is going to give us the sliding mesh. And match tolerance, the smaller the better. So 1e minus 4 is good. So we are keeping it. And its neighboring patch, the neighboring patch of AMI1 is in AMI2. The transform we have to put no ordering, and construct from we have to mention as patches. So these are keywords that you have to follow. And for patches, what is the patch that you are constructing from? Which is AMI, which is the first thing, this one. Then you go to the next where you say it is AMI2. The name is AMI2. So this will be acting as the master and this will be acting as the slave. So AMI2 is the slave. Patch info, again type is cyclic AMI, match tolerance is 0.0001, and its neighboring patch is AMI1 because the main is AMI2, so its neighbor will be AMI1. It's the opposite here. Transform will be again no ordering. The construct from is patches, it's a keyword, and the patch is AMI slave. So this is this. So what we are doing is we are taking the existing patch and we are converting it into master and slave patch. So how is this going to affect anything in the simulation? If you go to polymesh and go to boundary, open it, you can see that there is AMI and AMI slave, but this is named as walls. That is not what we want. We want it as cyclic AMI. So altering it manually is not a very good option. So what we will do is we will use the create patch. That's what we set up right now. So create patch, overwrite, enter. Just wait for the magic to happen. Now if you see in the last, you can see that the type is cyclic AMI in group one cyclic AMI, and it is mentioning everything. The neighbor patch of AMI1 is AMI2, and the AMI method is face area weight AMI, and for AMI2 the neighbor patch is AMI1. So everything is just set up very quickly. So all you have to do is set up the create patch dict, go here and run the command create patch space hyphen overwrite. Let's go to our allrun.pre. Everything is done except for this. So if you just copy paste this command in here, it will not work. So and do this command, enter. So that will basically copy the 0.original into 0, which is what we want, not the 0.original. Now let's see what is there inside 0. We'll do it differently here. Okay, in velocity, you can see the AMI1, AMI2 is set to cyclic AMI. You don't have to worry about it. Inside K also it will be cyclic AMI, in UT it will be cyclic AMI, everywhere it will be cyclic AMI. So you don't have to worry about AMI1 and AMI2. Let's look at fan. So fan is moving wall velocity, and we are giving it as 0. It will be moving, but on the wall it should be 0 because it is no slip. And for door, it is acting as sort of an input or inlet. So you can give a fixed value. It is saying minus 0.1 meters per second, and the outlet is outlet. Now let's just visualize all of these. So we have the mesh here, and let's look at the outlet. This is our outlet. This is our door. So we have the room and we have an outlet and the door. Door will act as input, and this will act as the outlet, which is like the outlet. Okay, and outlet is named as pressure inlet outlet velocity. Room is no slip because it's a wall. Desk is also no slip. Similarly, if you go to pressure, the door, since it is like the inlet, it is kept as fixed flux pressure, and the outlet is kept as fixed value of 0. That is like kinematic pressure. So we will define fixed value of 0 for atmospheric pressure conditions. For K, the door is kept as turbulence intensity kinetic energy inlet, and for outlet is 0 gradient. For nu T, it is door is 0 gradient, outlet is 0 gradient. For all the walls, it is unity wall functions. Similarly, for K, all the walls are just KQR wall functions. And omega is also like omega wall functions on all the walls. Outlet is 0 gradient. And the door, which is inlet, is kept as turbulent mixing length frequency inlet, which is like the most common ones. So these things are pretty straightforward and nothing special for this case, except for the cyclic AMI, which we define in every file as cyclic AMI. Okay, now that is out about the zero. Now let's go to our dynamic mesh dict. So inside dynamic mesh dict, the dynamic FB mesh solver is dynamic motion solver FB mesh. Okay, and the motion solver library, you have to mention it, FB motion solvers, and the motion solver is solid body because we are rotating a solid body. Cell zone is rotating zone because in the create patch on this SnappyHexMesh, we define it as rotating zone, and the solid body motion function is rotating motion. So the origin is the origin of the fan. You go here and turn on the data access grid. You can basically see the numbers here and calculate what should be the origin of this. By any chance, if you're not able to see any of the colors like me, you can go here and you can restore to defaults and you can see the numbers better. So if you see what is the origin, you can mention it here. For your geometry, while making the geometry, you can keep it as 0 0 0 for convenience. And the axis of rotation in our case is z, so z will be the axis around which it will rotate. So the 0 0 1 is mentioned, and omega is in radians per second. So if you give 10 radians per second, it will rotate in 10 radians per second. And you can put minus to reverse the direction. And that's it for dynamic mesh dict. If you go to gravity, it is again very straightforward. In z axis, we have minus 9.81, so it will be pointing downwards in z direction. So that is usual and nothing special. Okay, if you go to system, we already saw what is block mesh, create patch dict is done, decompose pair is done. If you want to ponder over the FP scheme and FP solution of the pimple foam, you can check it out. I'm not going to explain it. That's not the scope of this video. And we finish SnappyHexMesh dict and surface feature extract dict also. So let's open our control dict. Here you can see the application is pimple foam. The start time is 0 and end time is 1 seconds. So the delta t is set to 2e minus 4. Right interval is set to 0.02. Okay, and it is actually running adaptive time stepping. So adjust time step is set to x. So we have to define the maximum current number. It is set to 1 for convenience, and the maximum delta t is set to 1. So the delta t will not go above 1. It should not. So it will not go above 1 even in the worst case. So it will try to keep it less than that. And right control is set to adjustable just in case if we want to change the end time or delta t mid of the simulation. So this is also a very normal control dict. Now let's start the simulation. So I can do decompose bar, and to run the simulation we can follow the command mpi run np8 simple foam parallel. Press enter and wait for the simulation to end. It will end when it reaches a time of 1 second. I'll get back to you once the simulation is over. I actually stopped the simulation to show the further steps in post-processing. So let's assume that the simulation is over for you. I have run till 0.35. Okay, let's assume it reached 1 for you. And then you can follow these steps. So you have to do reconstruct par, enter. So the process is over for me. Now we don't need any of the processor files. So we can delete them. Okay, now we can open the para.foam file in ParaView. Just click on apply. Now by default it will have two. If it has only one, don't worry, we'll actually add a lot more. So let's assume that we are positioning it something like this. Okay, now let's start with the post processing. First, what we will do is we'll change the first one to solid color, and we will choose only the room, reduce the opacity, click on apply, hit this, use around zero point 0.2, it should be fine. To change the background color, edit, settings, color palette, and change this to white. Okay. Now in the second para.foam, what we are going to do is we will just select the door and the outlet, click on apply, and show, change this to solid color. I'm going to put this to black. Okay. Now you can go here, drag and drop this para.foam, click on apply, and for this you can select only the fan, click on apply, change this to solid color, and let us put some good color. Let's take this color, put one more para.foam, change this to solid color, keep only the desk, and give it a wooden color. I think this looks wooden, and apply. Yeah, that looks fine. So if you go to the first time step and click, you can actually see the fan is rotating. Yeah. Now what we have to do is add the streamlines. To do that, I have to add one more para.foam, click on apply, let this all be there, and click on streamlines. To change this to point cloud, just click on apply. Initially you will get something like this, and you can make the sphere bigger. One, yeah, that looks fine for me. Position it something like this, click on apply, change the color to velocity, or else you can change the color palette also. Let's say I'm just going to rainbow, and we can hide this color chart to this. Just press on this and it will be hidden, and you can actually increase the number of points maybe to 150, or maybe make it slightly bigger. Yeah, this looks fine to me. You can hide the sphere here. Then we can go to custom data range, put 0, something like 0.08. Now you will get something like this. You can play around the values for upper limit, and you will get something like this. You go to the first time step and hit on play, you'll get these. Now to save it as an animation, all you have to do is file, click on save animation, give it a name, and probably give like 5 frames per second and click on OK. That should give you whatever is there here. But I like to do something extra. Go to filters, search on tube. Okay, and click on apply, and just make the 0.005 or slightly bigger, 0.008. Yeah, and change this to velocity. or again the same thing. You can choose this rainbow and custom data range 0.08. Yeah, so now it will look more solid, and you can slightly reduce the opacity. This will look much better in my opinion. So it's a personal preference. It's up to you to do it or not. Now you can do the same thing. File, save animation, give it a name, put your desired frame rate and click on OK, and it will save the animation. Okay, now let's take a look at the animation. Click here and see that we got the animation. So that is what we intended to get. I hope it was clear. Now you can play around the position or angle or anything. So that is up to ParaView and nothing related to OpenFOAM. Now you can play around changing the inlet values or the RPM or adding more features to the geometry or anything. So if you have any questions, you can drop down in the comment section or mail us at codedynamics@gmail.com. If you liked the video so far, consider subscribing to the channel, dropping a like to the video, or any suggestions down in the comments. Thank you. See you in another video.